welcome to another episode of Coding Practice. Today I'm going to talk about another useful coding pattern, which is called topological sorting. So topological sort is used to find a linear ordering of elements that have dependency. For example, if you have some task that depends on each other, basically you have to finish one task and then start another task. These kind of dependencies are basically a hint for us, so that if we want to find a proper ordering of the task, considering their dependencies, it's good to think about topological sorting and see if it can help us. So let's see an example. Given the total number of courses and the list of prerequisites, return the ordering of courses you should take to finish all courses. For example, let's assume that we have 3 courses and the list of prerequisites is this. Okay, so based on the problem description, the pair of A and B means course B must be taken before course A. So basically we have to take course B and then course A. Now, in this example with 3 courses, it looks like the course 1 has to be taken before course 0, and course 2 has to be taken before course 1. Now, what's the proper order that we should take these courses to be able to finish all courses? So definitely we cannot start with 0 because we have to take course 1 first. And we cannot take course 1 before we taking course or passing the course 2. So the order would be, first we take course 2, and then 1, and then course 0. Okay, so we want to find this kind of ordering. This isn't a simple example. What about this example? So let's say the number of courses is 4, and these are the prerequisites. So again, I have to take course 1 before course 0. I have to take course 2 before course 1. And I have to take course 3 before course 1. So in this example, looks like before I'm able to take course 1, I have to finish or pass course 3 and 2. One possible solution or one possible ordering is I first take course 2, and when I do that, then still I cannot take course 1 because course 1 has another prerequisite, course 3. So I have to take course 3, and then I can take course 1 and then 0. Another option is first I take course 3 and then 2 and 1 and 0. Both of these options are valid. Let's consider another example. What if the prerequisite is this? Let's say I have 2 courses. Construct the directed graph again. So I have to take course 1 before I'm able to take course 0, and I have to take course 0 before I take course 1. Is it possible? It's like a egg and chicken problem. No, because I cannot take course 1 because I have to first take course 0, and I cannot take course 0 because before that I have to take course 1. So they depend on each other, and as you can see, there's a loop. That means there's no way I can pass these courses because they all depend on each other. And the answer is basically an empty array. I cannot pass all, and I cannot take these courses. So now that we understand the problem, let's see how topological sort can help us to come up with the proper ordering of these courses. So let's start with the first example. So it's obvious that I should start with the courses that do not have any prerequisites. Okay, so how do we detect those courses? So you see here, based on the graph that we constructed, we can actually see if a course has prerequisite or not by checking the in degree. In degree means the number of edges that enters the node. For example, this course 0, there's one edge is entering course 0, so the in degree of this course is 1. What about course 1? Again, course 1 has one edge entering to it, so again the in degree is 1, and the out degree of 1, the edge that is exiting node 1, is 1. But we're not, like in topological sorting, we are not considering the out degrees. So because all we care is the dependencies. We want to count how many prerequisites each node has. So, but what about this node, course 2? As you can see, there's no incoming edge to this node. So the in degree of this node is 0. Means that this node has no dependency, so we can start with this node. What about this example? Again, course 0 has one incoming edge, so the in degree is 1. For course 1, there's 2 incoming edges, this edge and this edge. So the in degree for course 1 is 2. In degree for course 2 is 0, and in degree for course 3 is 0. And it's obvious that we can start with either course 2 or 3 because they don't have any dependencies. Their in degrees are 0. What about this one? The in degree for 0 is 1 because it has one incoming edge, and the in degree for course 1 is also 1 because it has one incoming edge. And as you can see, there is no any element, or there's no any course with in degree of 0. So that means I cannot start with any node, and I cannot basically finish these courses. So in topological sort, what we do is we first construct the graph, directed graph, based on the dependencies or prerequisites. Then calculate the in degree of each node, and then we start visiting nodes with 0 in degree. And then we continue steps 2 to 3 until there's no node with 0 in degree. Okay, so now let's apply this topological sort algorithm to these examples. So as I mentioned, so we already constructed the graph, the directed graph, and we calculate the in degree for each node. Now we start with the nodes with 0 in degree. So let's have a queue, and I put 2 because it has 0 in degree in it. I checked my queue because I know that whatever is in my queue has a 0 in degree. So I pick them, visit them, and remove them from my graph. So the answer is this. So there's 2 in my queue. I pick them, I add it to my answer, and I remove it from my graph. When I remove 2 from my graph, I have to update the degree of its neighbors. The neighbor of 2 is 1, and when I remove 2 from the graph, then the in degree of 1 becomes 0, right? So I remove 2 because I already visited. I remove the edge, and now I have to update the in degree of 1. And now because 1 in degree of 1 is now 0, I add it to my queue. Now I'll go and check my queue again. So there's 1 in it. So I remove it, I add it to my answer, and now I have to remove it from my graph, and I have to update the in degree of its neighbors, which is 0. So now the in degree of 0 is 0. I add 0 to my queue. Now I pick it up, I add it to my answers, and I remove it from my graph. And there's no other elements in my graph. But as you can see, I constructed the answer. So what about this one? So again, I have a queue. I calculate the in degree of my nodes, and then I add the nodes that has 0 in degree. So there are 2. So it's 3 and 2. Okay, now I pick one of them. So pick 3. I add it to my answer. Then I remove it from my graph. When I remove it from my graph, then I have to update the in degree of its neighbors. The neighbor of 3, as you can see based on the graph, it's course 1. And so I have to basically decrease the in degree of course 1. So instead of 2, the in degree of 2 becomes 1. Then I check my queue. Okay, there's 2 in it. I remove it, I add it to my answer, and I remove it from my graph. And when I remove it, I have to update its neighbor's in degree. So the in degree of 1 is 1. Now I decrease it, and becomes 0. And since it becomes 0, I add it to my queue. I pick it up, add it to my answer, remove it from my graph, and update the degree of its neighbor. And because 0 has in degree 0, I add it to my queue, then I remove it, I add it to my answers, and I remove it from my graph. And here's the answer. So obviously at the beginning, when I had 2 elements in my queue, I could actually pick any of those, and still I had a valid answer. What about this one? So I constructed the directed graph, and then I calculate the degrees in degree of each node. And then, as you can see, I don't have any node with 0 in degree. So then my queue is empty. That means I cannot actually start with any node. So my answer is also an empty set. Now that we understand how the topological sort is working, let's actually code this problem up and see how we can implement the topological sort in code. Okay, so as I mentioned, we first have to generate the graph. So we are given the number of courses and the prerequisites. So we construct the graph, and then after that we have to calculate the in degree for each node. Calculate in degree given the graph. Okay, so let's implement these two functions first. Construct graph. It's number of courses, which is an integer, and then prerequisites, which is a list. And so since each course is represented by an integer, I can use array to represent the graph. So I say graph is an array of sets, and then for each A and B, for each pair of dependencies in prerequisites. So we know that based on, according to the problem description, B is the prerequisite of A, okay, for each pair of A and B. So I say graph of B, add A to its set, shows that B points to A. I guess that's it, and then I just return the graph. And for the in degree, my graph is a list, so in degree is, I initialize it by 0. Let's actually give the number of nodes as an input as well. Now I say for I in range n, in my graph for course I, I'll get the set or neighbors, and then for each neighbor in neighbors, I increment the in degree. In degree of neighborhood is 1. At the end, I return in degree. Why is that? Because my graph is like, okay, so course B is a prerequisite for course A and C, and then maybe course C is a prerequisite for course A, and then based on that, then the in degree of A must be 2, because A has prerequisite B and prerequisite C. So in degree of A is 2, in degree of C is 1, and in degree of B is 0. Basically this for loop just calculate that. Now I have the graph and I have the in degree. I mentioned that I have to have a queue, and then I basically push whatever node that has in degree of 0 into my queue. So say if in degree of I is equal to 0, then dq append I. Now that I have my queue, then I'll start picking up from my queue, add it to my list or my result, and then remove it from my graph and update the in degree of its neighbors. While queue, I get the node or course basically. I add it to my result, and then for each of its neighbors, I I decrease it there in degrees. And I check if the in degree is 0, then I'll add it to my queue. Then at the end, I just return result. Is it correct? No, because we didn't actually consider the fact that there might be some loop in my graph and I cannot actually take all the courses. So I have to check whether if the number of elements in the result does not match with the number of courses, it means that I could not actually pass some of the courses and I have to return empty. So I return result if len of result is equal to number of courses, else I return empty. So now let's test it. In this case, so course 0 depends on 1, course 1 depends on 2, and course 2 depends on 0. And as you can see, there's a loop, right? So I cannot actually pass these courses because there's a loop between the courses. So the output should be let's see. I guess, oh, sorry. Should add course in it. Let's run it again. Cool. Yeah, it's as we expected. The first example returns this. The second example returns this. Okay, looks it's working. What about let's actually briefly talk about the time complexity. So the time complexity is, so I'm actually checking every single node, every single course, and I actually check also all the edges, right? So the time complexity would be number of vertices plus number of edges. What about the space complexity? So output is O of n is the number of courses. In degree array is also O of n is the number of courses. But graph, basically in the graph, I have basically all the nodes and I have all the edges or the dependencies. So which is dominant. So again, the space complexity is O of v plus e, where v is number of courses and e is number of dependencies. Hope it was useful. Until the next video.